Okay, well, thank you again. So I have the luck here to be your last speaker of the morning here, so prevention and mitigation of heat damage. Oh, can you hear me in the back okay, like this? Okay. Okay, so weather conditions leading to heat events, heat wave formation. Typically we have these stagnant high pressure systems that kind of become stationary over part of the state, and that is what generates these high temperature systems. Danielle can't hear me in the back still. Can I just hold it? Okay, I'll do this. Similar to what happens in the winter, oftentimes you get that high pressure formation, the higher temperatures in the winter. Similar thing happens in the summer. As was mentioned yesterday, that we can relate the formation of some of these events to actions over the Indian Ocean to help predict them, which is hopefully a good thing for us. We went over yesterday a little bit the energy balance, and that comes into play here in our vineyards. The thing to keep in mind, the incoming energy, the solar radiation, that's the RN term there. That has to go into something. So it's either being used to evaporate water, that's the latent heat, the LE term, or becoming sensible heat, heating up the system, that's the temperature that we feel, or into the ground heat flux, but that's typically a smaller term for our uses, so I just put it in a small g. Primarily we're looking at this, dividing that incoming solar radiation into either evaporation of water or heating up through sensible heat. So one thing to keep in mind, our vineyards are very different from many other crops. Dr. Kitipau yesterday showed you an energy balance chart, and I even forget what the crop was. It could have been cotton or something. But the LE term, the energy going into evaporating water, was huge. The H term was very small. So in fields like that are well irrigated and have full canopy cover, a lot of the incoming energy is going into evaporating water. Okay? Then there's less heating of that system because you have a cooling effect instead of that energy going into evaporating water. Our vineyards, such as this one here, you can see the size of the shadow on the ground when the sun is overhead. There's a lot of dry ground surface which is exposed to sunlight, so that is not evaporating much water. There's maybe a little bit of evaporation, but really the amount of energy going into direct evaporation of water that's hitting that canopy is smaller than in most other crops that we grow, so that's something to keep in mind. And you can go out with a little ray gun, this is like an infrared temperature thermometer, and get a feel for how different these conditions are. So I'm taking a reading of looks like a little mustard weed there on this summer afternoon, and the reading of that canopy is 97 degrees, and I didn't get a reading of the air temperature, because it was a hot summer afternoon for me to do this. But then I take a reading of the ground surface that's over 150 degrees. So again, just sort of gives you the idea that this bare ground surface, when it's being impacted directly by sunlight in our vineyards, is generating, it's a very hot surface, and we don't see that in most other crops. And this is something that's been of interest to me, how that heated ground surface impacts air temperature. So for a number of years now, I've been putting out weather stations that look like this on the left that have air temperature sensors at different heights above the ground. So this is 1 foot, 2 foot, up to 8 foot above the ground. Otherwise, it's a fairly conventional system. But it produces charts like you see on the right, and that's just a pattern of air temperature in the afternoon compared to height above the ground. So you can see at the 1 foot height, that's much, much hotter. That's about 105 degrees roughly. And then as you go up in height, that air temperature rapidly diminishes, and you get up to, say, our standard measurement heights of about 5 feet, and it's about 7 degrees cooler. So that's a big difference in air temperature with a fairly short difference in height above the ground. And I note in that example, the wind was blowing at about 2 miles an hour. So even with this mixing of the air, you still get this stratification happening when you have that sunlight hitting a bare surface like that. Okay, as far as heat damage to vines, so our concerns, just very high air temperatures that are raising the temperature of the whole system, the whole plant system. The other issue is direct sunlight on berries, which Khan mentioned yesterday how hot these berries can get when they're exposed to sunlight, and he had numbers 120 or more degrees that these berries would be at. These conditions are exacerbated by vine water stress. So if the vines don't have enough water and they are shutting down their stomata in the hottest part of the day, you're reducing then the evaporation cooling effect, and increasing the heating effect in a vineyard. The other, when water stress is really severe and you get defoliation, then that's compounding all that even more. So you're reducing the cooling, the evaporation losses, you're increasing the sun exposure on the fruit, and reducing the size of that canopy if it's severe. So you'll have more problems going forward. So that's something we really need to avoid. And here's just an example of a classic production style on the Central Coast that we don't do as much of anymore, but it kind of embodies a lot of the challenges with growing vineyards this way and with respect to heat. So what you can see here, the fruit in this example is in some cases about 6 inches above the ground. So if you now compare that to the chart that I showed you, how air temperatures can vary with height above the ground, we're putting that fruit in some of the hottest air that exists, very near the hot ground surface. There's some defoliation happening. You can see that probably from water stress. There's a lot of direct fruit exposure to sunlight, and a lot of those berries are pretty heavily cooked. So this is kind of an example of the type of vineyard design here, which under a lot of our current conditions really is not suited to that type of environment if these high heat conditions are one of the main concerns. It should be grown in a different manner to try to mitigate that. That was a dry farm vineyard. This is an irrigated vineyard, but just as an example that sometimes problems happen that can expose us to some severe heat damage as a consequence. This is not routine management, of course. Something happened, I don't know what, in this site that caused them to suffer severe defoliation. Maybe a pump went out. Maybe a dairy and winemaker wanted to try something really pushing the boundaries of vine quality and wine quality and ended up with this. I don't know, but what the consequence we know is that now this fruit is heavily exposed to all this direct sunlight and is going to suffer consequences of that. As I showed you this morning, irrigation usage is highly variable in the area. So let's say, for example, that last slide corresponded to maybe somebody here on the very, very bottom of that. And there is actually a line here that kind of just flattens out, that somebody put on a lot of water early and then just stopped. Maybe it was that person who said, maybe something happened and ended up with that. So irrigation management clearly is key to help preventing that and to keeping a healthy foliage throughout the growing season that we want to help maintain that. So to put numbers into perspective in different growing regions, I put together this chart here showing you reference evapotranspiration from last summer, comparing Napa at the Oakville station, that's the red lines, and what I'm combining together daily values, that's kind of the squiggly line for each, and then an average drawn through them, a best fit line, that's the dashed line. The blue, then that's Paso Robles, and then the black line, that's Bakersfield. Okay, so clear pattern, you see that Bakersfield has a much higher reference evapotranspiration in the summer than we do here in the either Napa Valley, Oakville, or Paso Robles. But let me just separate this here, and now we can just look at Oakville and Bakersfield. And what I just want to point out is how erratic this is. Of course, we have those periods of much higher temperatures or much higher reference evapotranspiration. And I'll just draw your attention here to June 23rd. That's the highest peak. That was the maximum daily reference evapotranspiration in Napa, where that red Napa line moved up to Bakersfield line. So for one day in the Napa Valley, you had Bakersfield conditions here. Maybe you probably remember that, June 23rd. So that was a fairly extreme day. So now, clearly, irrigation requirements are changing with that reference evapotranspiration. But I just wanted to kind of point out what is driving that change in the value of the reference evapotranspiration. So go back to the CIMIS data from the CIMIS station at Oakville and just pulling out the solar radiation values. That's the blue line. So we're looking at actually a week worth of data that just goes around the June 23rd value, which I have in that shaded area here. So the solar radiation is the blue. And so the thing to note from the solar radiation, that really is not changing much throughout that week. There was one day, probably overcast, where the number went down, but it wasn't like there was some solar flare that led to a spike of solar radiation that led to the increase in reference evapotranspiration. It was the higher air temperatures. Okay, so that's just the key thing here, if it wasn't obvious before, is that when the air temperature goes up, the reference evapotranspiration also goes up. So it isn't just solar radiation that's driving that. Air temperature also has a role in that equation. So that's and this was on that station the hottest day of the year, almost 103 degrees at the Oakville station. So as air temperature increases, so does reference evapotranspiration, and this really is one of the key things. So the charts that I showed you for irrigation applications that I was studying in the Paso Robles area, if you notice during the summer, those lines were fairly straight. So if weather is changing from one week to the next, you'd kind of hope or expect that sometimes those lines would accommodate and respond to those changes in reference evapotranspiration. Straight lines might suggest that people are more on a calendar schedule. I don't know that. There could be a mix there, but one of the key take-home points, I think, from if you've suffered water stress, heat damage, then adjusting for reference evapotranspiration differences from one week to the next is a key thing. One of the problems that also people run into is that their irrigation system capacity does not allow them to do that, that the system was designed and they're operating it right up in its limit, that they really can't apply 25% more water, that they just don't have that ability to. I was looking at some data that another grower had shared with me. He's on one of those automated systems where he can watch his pump action online, and he showed me a chart, and I saw one pump was on the whole summer. It never basically turned off. So when you are operating at the limit of your capacity, you don't have much room to add more water. It's a little hard thing to do. So just keep that in mind, I think, going forward. If we're having to design irrigation systems for responding to extreme conditions, that's an important consideration. So other things that we can do, well, just reconsider how we're managing our canopies and our trellises to try to provide a bit more shading. You know, a lot of the vineyards that were planted in the Central Coast in the 90s, people copied what was being done in the North Coast, and those VSP systems down there suffered a lot of sunburn. So we've evolved now to systems like these. This picture on the left is a very typical type of management, where hopefully it's obvious here. The shoots are positioned on one side, so it's a half VSP, but then the other side is allowed to flop out and provide some shading. That's the hotter side. So that's an adaptation then to our conditions of having a bit higher temperatures. Definitely see more of these more sprawl type systems where now we're maximizing more of our shading of the fruit, and I think this will be something we see more and more, at least in areas that are most prone to suffering from the heat damage. This slide, the take-home message is that you have to grow enough canopy in the first place if you're counting on that to provide you with some shading cover for your fruit. So this was somebody who was trying to pay off the bank loan, I think, in the first 2 years. The vineyards set a lot of fruit on this little Pinot Noir, but neglected to realize that they needed enough leaf area there to shade that fruit. So there could be other factors, let's say nutritional issues, pest issues, nematodes, whatever, that's preventing your vines from growing adequately, which then indirectly is causing you to have fruit quality issues because you're suffering from heat damage on the exposed fruit. So those other things, correcting for them, might really help you address heat spike issues. Okay, so some things that we can do or keep in mind to help mitigate. An easy thing to help compensate for those occasional heat spikes is adding additional water, either with sprinklers or misters. You increase evaporation, reducing the air temperature in your system there, so very, very effective, we know that. And to point out, you're often not trying to irrigate, you're not putting on so much water that you're meeting the vine water requirements, you're just putting on extra water to help cool down the system. And a lot of that water's going to just evaporate rather quickly from the surface. So your application rate can actually be fairly small. But what does this require? Having a system that can deliver this water on demand, that can be a hard thing to have. Having the water in the first place. In many areas we just don't have an abundance of water quickly to do that with. The other thing you have to have is a quality of water that allows this. Some of us who are using groundwater that might be high in chlorides, you don't want to be sprinkling it onto a vine canopy because then you have toxicity problems. That water could be perfectly fine for drip irrigation. It won't kill the roots, but that same water on foliage can cause problems. So there's limits to using sprinklers in some areas. But misters that don't put that on the vine foliage might be perfectly appropriate. And that picture was from the Napa Valley. Making some efforts to increase ground reflectance. Well, one thing that we can do is manage cover crop residues to try to keep a light-colored surface here in the row middles, increasing the albedo and the reflectance of some of that incoming light. You know, imagine if we have a very dark soil, that if we tilled all this under and had a uniform dark soil surface, that could be quite a bit hotter than having a little bit of this cover crop residue maintained on the surface like that to try to increase the reflectance. Taller trellis systems. So that sad dry farm vine that I showed you that had the fruit down just a few inches above the ground level in the hottest air temperatures in that system, if we can just raise that up, this is about a 6-foot high wire here, that could be one way to help then just remove that fruit from some of the hottest air temperatures that we know are going to occur. There's other reasons why you might want to do this or might not want to do this. You know, I've been looking at these systems more from a frost avoidance standpoint, because on cold nights, the coldest air often occurs near the ground. So there could be other reasons why you might want or not want to do this. Another thing that we look at is row direction. So there's been a lot of work now, say, planting vineyards in northeast, southwest rows here in the northern hemisphere. What's the idea behind that? Is that in the hottest part of the afternoon, if you're managing like a narrow VSP canopy like this, that the shadow falls directly underneath that canopy, shading the fruit underneath that. So that's a logical way to help protect that fruit. So we see more people going in that direction. On the right here, that's just a picture of a row direction trial. I don't know if anybody's ever seen one of those. That's actually down in Argentina. I just think it makes a really neat display, and I was wishing their plot sizes were a little bit bigger so we can make use of Susan Oostin's tools here to actually track what is going on in that as far as temperatures and other things. That would be a neat way to do that, but the plots are unfortunately rather small. But that must be a nightmare to farm, whoever they have driving in and out of those rows. So I apologize if somebody now orders you to plant one of these because it looks cool from the air. So, but something to think about with this whole shift to row direction in that manner, okay? So if we orient these VSP rows to maximize shading of the fruit at the hottest part of the day, aren't we also minimizing the amount of canopy which is exposed to direct sunlight? I'll kind of show you a diagram of why that might be the case. And in so doing, maximizing the sun exposure of the row middle at that time. You know, I think we've looked at shading fruit as the primary goal, but in the process, we're also maximizing the amount of sunlight which is not falling on the canopy. And let me kind of show you in a diagram here. So imagine that you're the sun and you are looking down on one of these vineyards that's planted in that direction. It's kind of designed to sort of cheat you and to have the shadow fall directly underneath that narrow band of the row. This is what you see. You see these narrow green strips, and then in between them all the exposed bare ground or former cover crop, but it's a dry area here in California. We're not growing these vineyards with irrigated cover crop in between. There's no vegetation there for the most part. So I would think that in a situation like this, you're minimizing, if we go back to the energy balance concept here, you're minimizing this LE term, that energy that's evaporating water, but probably maximizing that H term, that energy that's going into the sensible heat term. So maybe causing more heating of the air within that vineyard. That could be a consequence of this orientation, even though you are now successfully shading the fruit. So you gain one thing, but maybe lose something else. But what if you oriented those rows in totally the opposite way, which we're not doing, because then that would expose the fruit to more sunlight? I think this is what the sun would tend to see under those conditions. Now you see the top of that bank of foliage, but then also some portion of the side. Okay? And under these conditions, because now you're exposing more of that canopy to the direct sunlight, you might be maximizing the LE term. More evaporation is occurring because there's more exposed foliage to sunlight, and minimizing the potential H term by doing that. And how might that affect air temperature? Now, I'm not suggesting you go and do this, tearing out all those vineyards and replanting them in this direction, but just keep in mind, when we change one thing, we often gain other things that we may not have thought about that might have a consequence too. So if you thought of vineyard foliage or canopies as solar panels trying to maximize the interception of light to generate power, this is how you would orient them. You would not put them up this way, because then you're missing that peak part of the day. So there is something to just keep in mind, is that the effect that foliage has on the environment, the temperature environment within that vineyard, is going to be impacted by its orientation to sunlight. So I hope that doesn't cause any ruckus. That's not my point here. Okay, other things that we can use: spray materials. Surround is one trade name. There's others like that. These are these kaolin clay materials that we can then spray on the vineyard here, acting as a sunblock. If you put a spreader sticker in with them, they will stick more to the berries if your goal is to try to then block some of that direct sunlight on the fruit itself. Without that, typically they don't stick as well. These products can work quite well, and they also have use, for example, in an organic vineyard as a leafhopper control material. But the biggest impediment that I've heard from growers, at least in my area, is that they just don't like the way it looks. If they spray this white film, and this is after I think at least 3 applications at this site that we had developed this kind of fully white cover, which you have to put it on fairly, a number of times to develop that full coverage. It just looks odd. So people are hesitant to use it really for just that purpose, even though I've seen people, organic growers, who totally lose their canopy because of leafhoppers, but yet they refuse to put this on, even though it might maintain that canopy. So again, one of those balance things. What is the worst of your evils? Would you rather put up the weird-looking vineyard with leaves, or a vineyard that you let the leafhoppers go and knock off all your canopy, but it looked, while it lasted, it was green? So that's kind of one of those questions. A number of growers throughout the state experimenting with shade cloth. This certainly has some potential for us to modify vineyards to help give them different types of light conditions on that fruit. Khan, who's not here right now, he's the better person to talk with. He's done the actual experiments with these types of materials to tell you what are the implications of putting them on. Talking to growers that I'm working with, they like the idea, they don't like the cost and the management effort that goes along with it. Questions about how long will this material last, will it cause other problems for them. But I think just over time, people will do enough experiments on their own to realize, is the cost and effort of this worth whatever return they get as far as crop quality, crop value that they're being paid to produce. So it's more of in some ways a grower issue to resolve that, to deal with their issues. But I want to talk a bit more about some of the temperature measurements and how we understand what heat conditions are. And maybe we can collect data in a little bit different way to help understand conditions a little different than we do right now. I've been doing work for a number of years with these black globe sensors. They're just a 6-inch hollow copper sphere with a temperature sensor inside of them. They're actually pretty simple. My interest initially was to use these globe sensors to estimate frost conditions. Okay, why is that? Because tissues like we see here on the left, these young shoots, their temperature at night is better predicted by the temperature of this black globe than it is by the temperature of a normal temperature sensor inside what we call a radiation shield. Why is that? Because tissues like this at night are exposed to outer space. They radiate heat into the blackness of space, whereas we put a radiation shield on a sensor to prevent that from happening. So we're measuring different things. The black globe is a better nighttime estimate of this tissue here. But the black globes are actually used as a daytime sensor for measuring human heat stress. Okay? So this is an example from a military device here. Here they have a small black globe. This is a little the Bear probe you see there. That's for measuring the air temperature. And then the gal here, she's pouring water into the wet bulb sensor to get the wet bulb measurement and the humidity from that. So this sensor, what the black globe is doing, it's a temperature that's influenced by solar radiation, so how strong is the sun hitting that, and also influenced by wind. So if you have strong light and no wind, that gets quite hot. But if you have cloud cover, the temperature of that black globe drops, or if there's any wind, that cools the black globe. So really it mimics, it's wholly designed to mimic what we feel during the hot part of the day, but it's also, I think, probably something fairly similar to what a grape berry would feel, because it's impacted by the same things. It isn't just air temperature, it's what's the temperature with the sunlight striking it, what's the cooling effect of the wind on that berry, so what's the humidity, and how does that affect transpiration of whether it's us sweating or fruit. So a lot of this data, I think, can be quite useful. And for that reason, why it's used by the military and by sports teams to help safeguard people. There are some weather station networks that make use of that. So Oklahoma has a very, very advanced weather station network paid for by petroleum money, I think. But they include all this black globe, or wet bulb globe temperature stress index. And this is just an example from one day in 2015, July 24th, 2015 in the afternoon. So where it's black, that's an extreme condition. You would not want to be outside doing much of anything. Red is a very high-risk condition here, probably not want to be outside working. And yellow and green are areas where maybe you can be outside, but still even be a little bit careful. So this is kind of, at a military base, they would say if it's red or black, you don't even be out, you're not even outside, because they don't want people collapsing doing their work. So we can use something similar for field workers, but we can also use this for, I think, better assessing what conditions might be affecting our fruit as well. So hopefully the accumulation of some data over time will help provide some insights into that. And then lastly, I just kind of wanted to wrap up here with just some thoughts. You know, we often inherit practices that we ourselves didn't decide to do. We sort of copied what somebody else was doing. A good example was that poor little vine I showed you that was planted a few inches above the ground. That person did not invent that practice. That person was just sort of duplicating probably what they learned from somebody else. That was common practice at the time. You know, another common practice, we've evolved now to these bands of VSP with our fruit underneath it. If somebody was to come into this industry, let's say, who previously made solar panels, and they looked at that and say, well, this is crazy. Why are you planting your solar panel leaves in that way? They might want to evolve into a different pattern now. Who knows what they might come up with? We have lots of money to develop some new type of trellis system that tries to increase the solar interception by that panel of leaves, or provide more shading, whatever, maybe try to raise things up higher. I'm inspired when I go down to Argentina, and Daniele mentioned this yesterday, some of these overhead trellis systems that they use. This is in Argentina, they're used in Chile and elsewhere, where these are traditional systems that really they accomplish a lot of that. You know, so these are vines where the foliage is up high off the ground, 7 feet, where they're now more horizontal. The fruit dangles underneath that shaded area. And if they're managed correctly, these can produce, you know, good tonnages and also very good quality. The downside, of course, hard to mechanize something like this. So that's why that hasn't transmitted, and why even people down there, these are not being widely planted. They're planting very similar systems to what we do. But I think it would be crazy for us to not at least remember for a moment where these do excel. Because if you're out there in the summer in a vineyard and they've got a block of this and it's a hot day and you want to have a conversation with somebody, you step under here because it feels nice. It's cool. It's comfortable. You wouldn't want to stand out there in some tiny little VSP vineyard because you're going to be quite a bit hotter and more uncomfortable. So there is some benefit to doing this. I'm not claiming that this is what we should do, but at least understand what the advantages were of this system. Okay. So with that, I think if I have time for questions.
This bad examples, but they were mainly designed for people to stay under.
To be comfortable, yeah.
Questions?
Anyone?
Yeah, have you looked at the effect of albedo of the soil on the heat of the berry?
Yeah, so yeah, the question is this albedo of the soil, so the reflectance of the soil surface on the berry heat. I have not. You know, what I would love to do is develop a sensor system that would mimic that, and allow us to then take measurements in different areas to get a lot of different types of measurements of that. So I don't know what that difference might be.
But the assumption of tilling the soil, by tilling the soil, you're saying it would increase the absorption of heat and storage.
Yeah, or at least heating the surface, making that the surface becomes very, very hot. in that system. So that is then warming the air that's near that surface.
I'm just wondering if the reflectance is worse or better.
Yeah.
Well, I
Be
have the
something
same
to-
question because when you have straws, especially when the cover crop is mowed, you got straws, so the reflection is also in many different directions. It's not only vertical, so you don't get rid of that heat. You just reflect, but it loses the intensity. Probably becomes, a long wave radiation after hitting the ground. But it's really intriguing what the effect of this increase of albedo. And I think it depends on the row orientation also, because you got the sun and at different angles with respect to the row orientation. So it could be a good research project. I have a question about the berms. So what is the effect of planting on berms with respect to planting on flat grounds when you don't have the cover crop? Does it make any difference at all for the air temperature profile?
So on berms, you mean like in this picture here, there's small berms that...
Well, you showed one of the picture that was like a VSP planted on berm with a taller canopy.
Oh, yeah, okay. Well, so let's say an issue is just whether or not there's a cover crop present. I mean, it depends on what's happening in the middle of the summer when we're having our heat spells and what condition that ground surface is in at that time. I don't know if that's...
No, there was clean cultivated with no cover crop.
Yeah. So, I mean, if it's just a berm, like in this picture, that's just raising a bit of a soil, I don't think that's going to have much of an effect at all for what conditions I'm looking at here for the temperatures. I don't know if anybody else has any input to... Okay. All right. Thank you. Oh, one more.
Yeah. So, Mark, I did some work up in Calistoga where I was looking at cluster temperatures, and I happened to, just out of interest, look at bare soil versus just a mowed cover crop, and there was at times about 20 Fahrenheit difference between those two rows at 2 p.m. during summer months. Have those stations that you have with the 8 feet, have you looked at that data to see if that seems to be the same similar case in summer?
So I'm with those stations, I'm not yet measuring ground surface temperatures. So, but you were measuring in the summer with live cover crop, green cover crop, or is it?
No, right. I
Right.
guess my question is, do you have that sort of set up in a tilled versus non-tilled?
Yeah, no, good question. So right now it's only in sites that have dry grass, similar to that's a lot of our common vineyard management. So finding sites with bare soil would be would be another measurement. Yep.
You talk only about the effect of temperature or solar radiation. Is there any data collected on the effect of wind on heat damage, like warm air, fronds moving? Because that's another source of energy.
Mm-hmm. Yeah. I'm not sure. So the advection input of heat, I don't know if somebody has done any work on that. That's not something I have looked into.